Let's get started then. All right, so welcome guys. This is the first session of the problem solving course. Typically, it involves math, data structures, algorithms, and a lot of coding. If you are a bit more experienced, I would recommend you to delve into design because that is what the industry looks for. And in either way, uh, whether you are planning to work in the industry or start something of your own, these are the areas which you will anyway have to focus on. The content, as you might be aware, is a little vast. The goals of this course, I want people to enjoy problem solving. That's the topmost thing, and that is what builds the passion, right? Otherwise, it will look very stressful. The amount of effort that you're going to put in is going to take you into a deep spiral. Whereas if you start enjoying it, the results are going to be very colorful. And I want you to see the relevance of math in computer science. Like, why is math important at all? And why that still remains the topmost priority for solving problems. And of course, we want to understand what are the data structures and algorithms out there. What is the use of each of those things? Why do they exist? How do we use them in what kind of scenarios? Last but not least, we have to be able to write correct code, efficient code, and elegant code fast enough, right, to fit in the interview setup. We'll also conduct these sessions in mock interview mode, right? So that you get used to the interview setup. You are comfortable when you walk into the interviewer's cabin. So I would like to double up as a trainer as well as an interviewer once in a while. All right. So these are the things that we need to kind of have at the top of our head when we are dealing with computer science. So far we are used to seeing 1,000 and a million and a billion. We should be able to think those numbers in terms of 2 power 10, 2 power 20, 2 power 30 because of the way our computer systems work, right? For example, if I say I want to design a Facebook, right? So the thing that you should now think about is, okay, if you want to have everyone on Facebook, then there are, let's say, about 7 billion people on this planet. The 7 is now close to 8 in terms of powers of 2, right? So you should think about it as, okay, 2 power 3 billion. And a billion here, you can see, is 10 power 9, which is 2 power 30. Right? So we are talking about 2 power 3 into 2 power 30 people. So 2 power 33 people, right? And then if you want to save some very basic information about everyone on this planet, if they happen to join Facebook, let's say, right? Let's say we give a KB of data to everyone to create their own profile. Nothing fancy, very simple, right? So KB is another 2 power 10. Right? So we have 2 power 10 times 2 power 33. Right? So you have 2 power 43 bytes of data right there, which is nothing but 8 terabytes of data. Right? So let's look at some benchmark. If you look at your laptop, modern laptops typically come with a terabyte hard disk. Right? So we're talking about roughly 8 hard disks, assuming we even get 1 terabyte just for data. Right? We need just 8 laptops to store the data. If we create a global Facebook where we just give 1 KB of data to every participant, right? So that is how these numbers, these powers come into picture, right? You should stop thinking in terms of 10 parts and start thinking in terms of 2 parts. All right, we must have seen these formulas before. 2 power a times 2 power b is nothing but 2 power a plus b. Right? And then 2 power a whole raised to the power b is same as 2 raised to the power a times b. Okay, so a little bit of math there. Now let's get directly into the asymptotic notation. There is a nice link there that I have left. If you want to dwell deeper, we can go through the Khan Academy links, but we'll cover whatever is needed in this class. let's say we have the x-axis, which basically denotes the input, right? And we have the time on the y-axis, right? So as the input is increasing, the time taken to perform the operations of some algorithm, right, to run the algorithm is also increasing, right, some function. So let's define this function as, let's say, 3n square plus 8n plus 5, right? So if the input size is n, the time taken by the algorithm is 3n square plus 8n plus 5. Now, if you observe, right, we can try to put a bound on this. Right? We want to basically find out what is a nice curve which can neatly bound this from the upside or from the downside. Right? We look at both. So this can be thought of as, okay, this guy is less than 8n square, right, plus 8n square plus 8n square, right? Assuming n is positive, you can see that this term is less than 18 square. So this term is also less than 18 square. And this term is also less than 18 square. Right? I'm just taking the largest coefficient here, and then they're just putting it in front of every term there. And then I'm raising the power. Right? So which is like, so this original guy is less than 24n square. Right? Fair enough. So this function, the original function, can be written as less than some constant of n square. Agreed?
Yes.
Right? So you take the largest coefficient and then just do this thing here, what I did here. So this way of representing is quite convenient for computer scientists to communicate. Why? Now they simply have to say whatever you're trying to do is an order of n square, because it can be expressed as some constant times n square, and it will always be less than that, right? Which means there is a function n square which is kind of bounding this from the upper side like this, right? So this is your c n square, some constant, doesn't matter, right? So in the computer science world, we simply say that this is of order n square, big O. So as long as you can find a constant c which will bound this function from the upper side, we can say this is the order of n square. Right? Likewise, you can have a function on the lower side like this, and say, hey, whatever you do, this guy has to be doing at least these many operations. Right? So this is upper bound, this is the lower bound. Right? And this is known as the omega. This is the omega function. This is the lower bound. And there is a theta asymptotic notation, which basically says that it is a tight bound. So from the upper side, it is bound, and from the lower side also it is bound. So that is known as your theta, sometimes known as big theta. Right. So this upper bound is big O, the lower bound is your omega, and your tight bound is your theta. Okay. So let's look at an example. For example, let's say we want to find an average of all numbers in an array. Right. So there are some numbers. Right? So these are your numbers. You have to find an average. You have to find the average of these numbers. So what do you do? What is the algorithm to find average? You begin with the sum as 0.
Divided by number of digits.
Right. So sum is 0. You initialize sum to 0, right? And then you say, okay, I add 3 to sum, then 4 to sum, 1 to sum, right? The sum keeps on increasing, and you hit the end and you stop, and then you divide it by the number of numbers, right? So you tell me, what is the complexity of this algorithm? How can we express that in terms of n? So n is the length of the array, the number of elements.
complexity would be 1.
1 would mean that it will take only one operation or some constant operation. That's not the case, right? So if n increases, if the number of terms increase, then the number of operations you are performing is proportionate to the input, right?
Then it will take around n, right?
N. It must be N.
Big O of n, right?
So let us go back to the definition now. So big O says what is the upper bound, meaning you will not take more than that, right? So in this case, what will it be? Like, what is the upper bound here? Will you ever have to look at more than n numbers?
No.
No, right? So that is the upper bound. It is bounded by n, right? What is the lower bound?
1.
What is the minimum number of numbers you have to look at if there are n numbers to find
2.
out? No, but how will you find average with 2 when there are n numbers?
You still need to look at all the elements, right?
Right. So you still need to look at all the elements, right? If the lower bound is still omega of n, because there's nothing better you can do, right? So which means the worst case and the best case are still the same. So it's basically a tight bound, a theta of n. It doesn't matter, right? Whatever the numbers are, you still have to go over all the numbers. You cannot avoid going over all the numbers. So the worst case is also going to be order of n. The best case is also going to be your omega of n, which is, in other words, it is a theta of n. It is bounded by n itself, right? Is that clear? Let's take one more example. Let's say I want to search for a given number in this, right? So this is your average. This is your average, and average, right? Now I want to do a search. I want to search for a number in this thing. So you tell me what can be the worst case if I have to search.
Worst case is O of big O of n.
Big O of n, because
The array is not sorted, and at the most we might have to go to the last element, right?
correct. In the worst case, we may have to look at every element. So fine, big O of n.
Yeah.
That is the complexity of search. Then what else can we say? What is the best case?
1.
1
Constant.
is
First one.
point at the first position.
Right. So it could be at the first thing itself. So I can say the best case is 1. It is lower bound by 1. So at least one search you have to do. That is what it means. In the average case,
n by 2.
yeah, so like somewhere in the middle you can find, right? N by 2. So you can probably say it is upper bound by n, lower bound by 1. On an average, you may still take half of n, which is n itself, because we ignore all the constants. You remember? Like when I say Cn, we drop the C silently. That C could be a fraction or it could be a multiple. Right? So this is the worst case. You look at everything. Is the best case, only one guy. Average is n by 2, which is like we are trying to find the theta, the tight bound. So theta of n by 2 can be thought of as theta of n. Fair enough? Now, the most widespread asymptotic notation is big O, because we are mostly interested in the worst case, not in the best case, not in the happy case, right? Because happy cases may turn out like this. So what do I do with this? It's not very useful, right? And this guy anyway is looking closer to this guy in most of the cases. So why not just stick with the big O notation? So in the industry, whenever you talk about complexities, you are invariably talking about the big O notation, and people just drop the theta and omega. So they don't even talk about it unless they are from academic background. People even don't even remember the definitions of this now. Right? They just talk about big O notation. All right. Any questions? All right. So this is the chain that I want you to remember throughout the course. Right? Order of 1, a big O of 1 is the constant time. It is known as constant time. Right? So if you have to do, let us say, 1,000 operations, regardless of the input size, then it is still a constant algorithm because it just takes 1,000. Right? N may increase, but it is still 1,000. Right? N may become 1,000,000, but still you're doing 1,000 operations. So that is a constant algorithm. So order of 1 doesn't mean that it is taking one operation. Order of 1 means it's a constant time. It is not dependent on n. It is not changing with regards to n. And the next one is order of log n. This is a logarithmic function which many people tend to miss the essence of, right? Which is slightly worse than the constant time algorithms. Right? When I say order of 1 is less than, I mean the time which is taken by constant time algorithms is less than the time which is taken by the logarithmic algorithms. So it is actually better than the logarithmic algorithms. So let us look at what is a logarithmic algorithm. Let's take an example. Let me take a tree, a BST, which we'll delve into in future sessions as well, which looks something like this. Let's say there is a node 10. Everything to the left of a node is less than this number, and everything which is to the right of the node in the entire subtree is greater. Right? That's the definition of a BST. So right to 6 is, let's say, 8, and this is still less than 10, right? Because it is in the left subtree of 10. Right? So this is a valid BST so far, and this one. So anything to the right of 10 should be greater than, right? So this entire subtree should be greater than 10. But since it is to the left of 20, it should be smaller than 20, but greater than 10, right? This could be this. Anything to the left is smaller than a node, and anything to the right is greater than the node. And this property holds at every node. Right? That is a BST. Sometimes you have a strict relationship like this. Sometimes you say less than equal to and greater than equal to. Fine. Now, what is the complexity of finding a number in a BST? Right? Assuming this is a tree which is full at all levels. Right? Assuming if they have like this. Right? All leaves, all levels are, let us say, full. There are nodes here. So what is the complexity of finding a number in a BST? So let's say we are trying to find 13. Right? So what is the algorithm? You begin at the root. What do you do?
Compare at the root level.
Right. So what do we do? We compare with 10 with 13. Then?
As it is greater number, we go to right side.
Correct. So when you are going to the right, what is happening to this entire subtree here?
Left side can be ignored.
Right. So you see this left subtree is roughly half of the entire tree.
Yes.
Correct. So this is just the double of this, right? So we are ignoring half of the tree in one iteration. And this guy is gone. Okay. Now let's see.
Yes.
We came here, right? We came here. Now we are looking for 13. What happens now?
We go to left side as 13 is smaller than 20.
Right. So what happens to the right subtree then now?
Right part can be in the same way ignored.
Correct. So what has happened to the problem? Right? Your problem became half in one step. In another step, it became another half.
Again.
Right. In another step, it became another half. This will go on and on and on until you hit 1. There is no node left. There is only one node left where you decide whether that guy is there or not. This function is nothing but your logarithmic function. This is log n base 2. So how many times you can divide n by 2? Keep on doing it by 2, by 2, by 2, by 2, by 2, by 2, by 2 until it becomes 1. That is the inverse of your exponential function. Right? So what is log 8 base 2? How do you evaluate log 8 base 2? 3. So how did you get that 3? So you would have written it like
8
this, right? Log 2 power 3 base 2. Then you would have got it here, right? This is how we learned what logarithms are.
yes.
Log 2 base 2 is 1. But if you really think about it, we are saying I want to keep dividing this number by 2 until it becomes 1. Right? So I first do 8 by 2. Right? I get 4. I get 4. And again I want to do by 2. I get 2. Again I do by 2. I get 1. So I stop. So how many divisions did I do? 1, 2, 3. So this is what a logarithmic function is. It's actually the inverse of exponentiation. So if you see, how do I get 8 from 1? I double it. Then I double it. Then I double it. Right? So how do I get 1 from 8? Well, I divide it by 2. I divide it by 2. I divide it by 2. Right? So exponentiation and logarithms, they are actually inverse. Right? So this is a very important notion that one has to remember when you're dealing with algorithms. It just simplifies your life when you try to evaluate the complexities. Right? So now, what is the complexity of searching a number in this tree? Like 13, we started.
Log n.
Yeah, it's log n, right? Log n base what?
2 is default, I guess.
Well, it's not default. There's a reason for that, right? Because you're dividing the problem into two parts,
Left and right side too. Yeah, yes.
right? So that
Only two sides.
yeah, that 2 is not magical, right? That 2 is not magical. That 2 is there because of some reason. We are breaking the problem into two parts at every stage. Right? We are ignoring half of the problem at every iteration, which is why it is base 2. Right? So in computer science world or in normal world otherwise as well, we tend to deal with yes and no more than maybe option. Correct? Which is why you have two options. Right? That base 2 has become so ingrained because we don't have the maybe option. Let's take another example. If this is clear, this part is clear. Like how is a search
Yes.
of a number in BST log n base 2? Okay, let's take a. Let's say I have a scale, a balance. Okay. I have some coins. I have, let's say, 8 coins. Okay. Now I need to find the coin which is slightly heavier than the rest of the coins. So basically, what I'm saying is there are 7 coins which are of same weight, and the 8th coin is slightly heavier than the other. Right. So one coin is heavier. So how do I find that guy? And I have a scale here, which I can basically put coins here and then see which plate is going down.
You can use simple, I guess.
Again, log 8.
How? Like how do we divide? Like what is the best algorithm that I can come up with?
You put 4 in one and 4 in the other, and then whichever is heavier, then you take that and again split it into 2, and then keep going until you find the heaviest number.
So basically you took 4 and 4. Let's say if, this was heavier. Once again you take this 4, you split it into 2 parts, right? So you get 2 and 2. So again you decide which one is heavier. Again you pick 1, 2 and then 1 and 1, right? So how many comparisons in total?
Log to the base 2, right? Of number of, 3.
Log n base 2, because we are splitting the problem into 2 parts. At every stage you are reducing the problem into half. Correct? Which is why this 2 is coming.
Yes.
Can we do better? What are the options that we have? Do we have to compulsorily weigh every guy, or we have a choice of not participating in the weighing?
Yes, we have choice, I guess.
Yeah. So let's see how it looks, right? What happens if I actually do this? I break the number of coins that I have into 3 parts, let us say, roughly. So I get this 3, 3, and 2 guys just sit on the sidelines and watch what happens. Right? So what can be the outcome? Like I took 3, and I left the 2 guys here. They are not participating in the weighing. So what can we do next? What is the outcome of this weighing?
If both the three,
the heavier coin must be other two separate coins.
Say it again.
If both the 3 coins, each of 3, if they weigh same, then the heavier one must be among the left out the 2 coins.
Correct. So if they are same, then I can throw the 2/3 of the problem. Correct? These are 2/3 of the problem. 1/3 of the problem is sitting here. Correct? So if these are same, I throw away all these 6 guys. I don't need them because the answer lies here in 1/3. Yes or no?
Yes.
What if one of them is greater? What if this guy is way heavier than this guy? What can I say?
In one comparison, we have only 3 coins in which we have to find the
Right. So again, which means we can throw away these 3 and these 2. The answer does not lie here. Does it make sense?
didn't quite get it. Can you repeat? So basically, if one of the 3 is heavier, then it has to be one of the heavier one, right? Then we have to look at those 3.
Correct. So my claim is the heavier is actually in those 3 only. The heavier cannot be in these 2 or in these 3.
Yeah, that's correct. Yeah.
Right. In other words, I am again dropping the 2/3 of the problem here. Right. What is the 2/3? This is the 2/3. Let me highlight it here. So this 1/3 and this 1/3 is dropped because this left 1/3 is heavier, because the answer has to lie here.
Yeah, that's correct. Yeah.
Correct. So what is happening is, in any case, whatever happens, you reduce the problem to 1/3. If they are same, then you drop the 2/3 which have gone into the weighing scale. If they are not, then you drop the other party and the guy who is sitting on the sidelines. Right. So then what is happening to the problem? So again, this was heavier. So I take 3 coins, I break them into 3 parts. I repeat the algorithm. Right. I put 1 coin here, second coin here, and third coin on the sidelines. Right. So this algorithm also works. Right. So what is the complexity of this algorithm? If you're convinced that this thing works, what is the complexity?
2 comparisons.
Right, but in terms of n, what is the complexity? Of course, the number of comparisons have reduced from 3 to 2.
It's, I think, log to the base 3. Then
Log n base 3, because we are breaking the problem into 3 parts. Like every time we reduce the problem to 1/3. Right. So which is why heavier exponent, heavier base here means the faster the problem dies. Right. What is log n base n?
1.
1, right? Because we are actually breaking them into n pieces, n by n. Like only in one go you can reduce n to 1. Right? So we have to look for those when you're solving problem. How can I break the problem so fast that it hits 1? There is nothing much. It becomes trivial. When I say 1, basically it becomes very trivial to solve. In this case, there were 8, right? So we are basically talking about log 8 base 3. So how many times I can divide 8 by 3 by 3 by 3 until it becomes 1? Right? Couple of times. Right? Because 8 by 3, and again, if you do by 3, so now this guy is 9, this is 8, so it is less than 1. So just a couple of times is good enough. Right? So you have to know what is the idea behind the log n base 2. So that base 2 is not a magic, as I said. It depends on the kind of problem that you are trying to solve. right? How fast are you narrowing down the problem defines the base of the logarithm. Okay, so if you have no questions, let me take another example here. We do binary search, right? We do binary search. What is the criteria for a binary search to work?
Search it.
If you have to do a binary search, there is some criteria for binary search to work.
The
Should be
search is the
sorted.
middle.
It should be sorted in some
Oh.
ascending or descending order, correct? So,
Yeah.
so how does the binary search work? If I want to search for 5, what do I do?
Break down into half.
So I go to the mid location, right? Let me ignore the indices for a while. Yeah, 4 on this side, 4 on this side, 8, right? I compare 8 with 5. What do I do then?
Based on
If
the
it is less,
position,
then come to the
left
left
side.
side.
Right. So if it is left, you have to go to the left side, which means what happened to this guy?
Ignored.
Right. So half of the problem is dropped. Right. And the same algorithm repeats. Now once again I go here, whatever is remaining, I look at the middle of that guy and either go to the left or to the right. Right. So again another half of the existing one is lost. So it becomes this. So what is this function? Until it becomes 1.
Log n base 2.
Log n base 2, right? That is the complexity of your binary search. So you don't have to by heart anything and remember, okay, this is that, right? So you have to build an intuition when it comes to finding out the complexity of your algorithm. Okay, so logarithms are fairly clear now, I hope, the logarithmic function. Now, if you see, obviously, it is better than linear function, right? A linear is basically going over the entire data set. Order of n is basically going over the entire data set, right? Like we saw the example of finding the average, right? We have to go over all the numbers, add them up, and divide it by n. You don't have a choice. Right? So that turns out to be a order of n algorithm. Or you want to find the maximum in a unsorted array. What do? You go over all the elements one by one. You find the maximum. That is a linear. What is the complexity of finding maximum in a sorted array? Order of 1. So you just return the first guy or the last guy depending on how they are sorted. It's a constant algorithm. So the best case is also 1, the worst case is also 1. Right? If you are very particular about it, you can probably say it is a theta of 1s, tight bound. All right. So this terminology you have to remember. People use this terminology sometimes when you read books. You should not like be lost about what is this constant, logarithm, linear. This is logarithmically linear or whatever, right? Or sometimes just say n log n. Right? Again, there are classes of sorting techniques which depend on comparison, which you cannot do better than n log n. So whatever sorting techniques you have, which do comparison, right? They take at least n log n time in the worst case. That is. Right? So let's take a few examples. Let's say our numbers are in the range 1 to 100. Okay, I tell you that my numbers are in the range 1 to 100. The numbers themselves may be a million, right? So there are a million numbers, but they are in the range 1 to 100, right? And I want you to sort them. I want you to sort them. So how do you go about solving this problem? Right? So numbers are in the range 1 to 100. So let me write some examples. So on. right? So what is the best way you can sort these numbers? Well, anything, whatever sorting techniques you have been using so far, we can use that. Like, let's say today, you guys are familiar with coding to some extent, right? So how do you approach any coding, any sorting problem? We'll discuss the pros and cons, right? So that is just a debate.
How do we sort, right?
Given these criteria, right, that our numbers are
Arrays,
small, but the count itself may be a million.
I was using arrays dot sort.
So do we know what algorithm does it implement? So you're talking about Java, right?
No, not.
Or are you talking about Python?
My code in C#.
C#, fine. Let's see if C# they document what algorithm they use, right? What algorithm does arrays dot sort use? C#. Right? We'll look at the same thing for, let's say, Java, right? Arrays dot sort algorithm. This method uses the intro sort algorithm as follows. If the partition is fewer than this, it uses an insertion, so blah, blah, blah. And so people have asked that question here, right? So these are all interview stuff, right? So when you're mentioning something, the interviewer would be interested in seeing, hey, how deeper did you dig into it, right? Do you even care, or did you even bother to just see what the documentation says? Right. So why arrays.sort is quick sort algorithm? Why not another? So this is probably Java. I'm assuming this is Java. Okay. Now they are saying, okay, quick sort uses n log n and blah blah blah. Fine. What about C#? It uses quick sort algorithm, right? And they're given a source for it. Like where does Microsoft mention they use quick sort? Right. So if you see here, what does it say? It says, okay, if the number of elements are less than, then I use some sort. Otherwise, I use a heap sort. Otherwise, it uses a quick sort. So what is the time complexity of using this arrays.sort on our data set that we have here? Like, what would it eventually end up running? Which sort? According to this quick sort, right? If the numbers are large, like if the n is large, so it seems to fall in this bucket. And likewise, looks like Java has made up its mind that they also want to use quick sort. So the complexity that the library is giving you is order of n log n, right? Are we on the same page?
Yeah, that's correct.
Right? Everyone agrees that if you just go use the default library function, whatever favorite language that you are using, right? If you just call the inbuilt sort, looks like people are the developers have implemented a quick sort, right? Which is n log n implementation. So we'll implement actually a quick sort later when we come to divide and conquer. So quick sort is a well-known method which takes order of n log n in average cases. Fair enough. So, but can we do better? Can we do better than n log n? How do we use the fact that I gave you this, the range of the numbers as 1 to 100? Now, what if we allocate an array of size 100, let us say 1 to 100 or 0 to 99? It's up to you. Let us do the right thing. Let's do 0 to 99 because most of the programming languages begin with the 0 index. So what I suggest we do is take the first number, go to the index minus 1 and increment the count. So initially everything is initialized to 0. Everything is 0 here, right? I go to that particular cell and say, okay, I found a 1. So I go to index A1 minus 1, which is A0, and increment the count to 1. And everything else is 0, 0, 0. Then I get 2. Okay, I go to the index 1, right? And then I increment, I bump up the count to 1. Then again I found 100, so I go to 99 and say it is 1. I found another 100, so again I go to 99 and I bump it up to 2. Right? You see what I'm doing here? I'm just keeping track of how many times each of these numbers in this range 1 to 100 has occurred using this temporary array here. Yes, I'm going over all the n numbers and I'm keeping track of how many times each of those guys have occurred. So every time a number occurs, I'll go to its corresponding cell and then I say, okay, plus plus. Initially everything is 0. So instead of going from 1 to 100, because the arrays begin from 0 indexing, I'm going from 0 to 99. So this 1 maps to 0, 2 maps to 1, 3 maps to 2, 100 maps to 99. Is the algorithm clear? Is the idea clear?
Yes.
Right?
Yes, yes.
It's counting sort. I'm just counting the number of times each of these guys have occurred in the array. So once I have that count here in the array, then I can simply print them. No? Those many times I can print. So if I have 1 in 0th place, it means 1 showed up 1 time. If I have 1 in one location, then the 2 came up as 1 time. Right? These are actually the counts, the number of instances of the numbers. So I just have to print those things there. Right? If I have like something like this 1, 2, 3, 9, 10, 5, 4, like that, right? So these are the counts of the number of instances. So 1, this is actually in 0th index, 1 came 1 time, so I print 1, 1. And then there are 2 2's, right? And then there are 3 3's. Then there are 9 4's, right? So on. So I just sorted this thing. Yes, counting sort. I'm basically counting them because I know that the numbers are small. Right? If the numbers were, if I don't know anything about the number, right? Which is what your algorithm, which is what your library will assume, right? When they implement this here, they don't assume anything about the number. The number could actually be as big as the integer size itself, right? 2 power 32. Right? Which is the reason why this counting sort does not work, because now if I have to do counting sort based on the numbers magnitude, then this array that I have here, this has to be 2 power 32 elements, right? A valid integer value, if it is unsigned, can go from 0 to 2 power 32 minus 1 if it is unsigned int. We'll talk about it when we talk about more about the bit fields, the bit manipulations. When we come to that phase, we will see. Remind me to prove that this is the case. But in any way, if there was no property associated with this, I would have to end up allocating this big memory. Like, what is 2 power 32? What is 2 power 32? Let's go back to our deck. Here. What is 2 power 32?
Okay.
2 power 32. So where is the 2 power 32? Which bucket?
Between giga to tera.
So here, so 2 power 30 is giga. So 2 power 32 is 2 power 2 into 2 power 30. This formula. Right? A is 30, B is 2.
Okay.
Right? Which means it is 4 giga. 2 power 2 is 4. So 4 giga locations, 4 billion locations are required to do a counting sort if nothing is told about the numbers. Right? And that is supposed to hold a count of how many times that has occurred. So if that is another integer, so we are talking about a 4 giga integers. So each size of an integer is again 4 bytes. Right? So we are talking about a 16 GB memory to hold this temporary array. If we want to use the same counting technique on any range possible, right? Which is why it is very inefficient. You cannot assume that the system will have 16 GB RAM. Or if you want to use virtual memory and do whatever the OS does today, you end up doing swapping. A lot of the memory will be just returned to the disk and loaded from the disk. Which is why the counting sort is very inefficient. Right? Nobody implements that in practice. However, if you know the properties of the numbers, like I said here, I told you that the number n lies in this range, then you can happily do the counting sort. You can just have a temporary array and then you count every time it occurs, go to that particular cell and bump up the value at that cell, saying I found this guy one more time, I found this guy one more time, one more time, one more time. So you go over all the numbers, then you have all the counts in the temporary array, you simply print them one after the other. Okay, so think about the complexity. What is the complexity of this?
Complexity would be n.
This order of n because what are we doing? Like, right? You allocate a memory of 100 locations, which is a constant time, right? It doesn't matter, right? 100 is a constant. It's not depending on n, which can go from a million to billion. It is constant 100. All of them are in the same range. So it's in constant time you allocate memory.
Yes.
You in constant time you make all of them zeros, and then you go over each number one at a time and map it to this array. So the cost is basically going over the million or n numbers, right? Mapping them here, a million operations, which is nothing but n. And then you go over the 100 locations once again and see what is the count and print the guys so many times, or sort them, whatever. Right? So it's basically order of 100, which is 1, order of 1, order of n to map, and then going over this again, order of 100, which is 1, and then printing them in order of n time. So it is nothing but order of n. Right? You allocated memory for 100. You went over the numbers, order of n time. You map them here. Right? You once again went over the array here, and then you printed them so many times. So this is nothing but this is a constant. This is a constant. This is order of n plus order of n, which is 2 times order of n. But by definition, we drop constants when you talk about big O, right? So we drop 2 as well. We simply say it is order of n.